Welcome to A-Level Chemistry. Today we'll be revising chapters 2, 3 and 4. Let's start off with an example. Here is the lithium atom. Let's take a closer look. In the middle we have the nucleus. It's made up of protons and neutrons. A lithium atom has 3 protons and 4 neutrons in its nucleus. So let's have a look at the proton. It has a relative mass of 1. An actual mass in kilograms of 1.62 times 10 to the minus 27, a relative charge of plus 1, a charge in coulombs of 1.62 times 10 to the minus 19, and is located in the nucleus. Now on to the neutron. We have a relative mass of 1, a mass in kilograms of 1.62 times 10 to the minus 27, a relative charge of 0, a charge in coulombs of 0, and is also located in the nucleus. But what's this? And this? And this? These are electrons. Let's have a look. They have a relative mass of 5.62 times 10 to the minus 4, a mass in kilograms of 9.11 times 10 to the minus 31, a relative charge of minus 1, a charge in coulombs of minus 1.62 times 10 to the minus 19, and is located in the outer shells. So, our lithium atom has 3 protons, 4 neutrons, 3 electrons. But why? The overall charge of an atom has to be 0. All atoms are neutrally charged. If a lithium atom has 3 protons, all with a charge of plus 1, it means that they have a total of plus 3, and 3 electrons, all with a charge of minus 1, which have a total charge of minus 3, 4 neutrons, which all have a charge of 0. 0 plus 3 minus 3 equals 0. They all have to balance out. So lithium has a mass of 7. This is called the relative atomic mass. It's made up of the total protons and neutrons. Electrons are too small to really count. But hang on. If we look at the periodic table, yes, we see lithium has 3 protons, but it has an atomic number of 6.9. 3 and 4 equals 7. So where's the 6.9 come from? That's where isotopes come in. An isotope is an atom of an element that has a different number of neutrons in its nucleus, but the same number of protons. Remember, if the proton number changes, the element changes. An element is determined by how many protons it has in its nucleus. Here we have an atom of lithium-6. We have 3 protons, 3 neutrons, and 3 electrons. So 3 plus 3 is 6. Lithium-6. Now we have lithium-7. We have 3 protons and 4 neutrons gives us 7. So what that 6.9 in the periodic table means is that we have X amount of the 7 isotope and Y amount of the 6 isotope. In nature, 7.59% of all lithium found is lithium-6, and 92.41% found is lithium-7. If we times these percentages by their relative atomic mass and add them together, we get 100% 6.9. These percentages are the relative abundances of these isotopes, and 100% of it gives us the relative atomic mass, which we find on the periodic table. The relative atomic mass is the weighted mean mass of an atom of an element compared to 1/12 the mass of a carbon-12 atom. The relative isotopic mass is the weighted mean mass of an isotope of an element compared to 1/12 the mass of a carbon-12 atom. But now let's have a lithium plus ion. So with an isotope, we had same number of protons, different number of neutrons. Now with an ion, we have a different number of electrons. Here we have 3 protons, 4 neutrons, and 2 electrons. 0 plus 3 plus minus 2 is plus 1. So we have a lithium plus ion. Let's look at another example. Here we have sodium. Sodium has 2 electrons in its outer shell, and now we're going to take them away. We've taken away 2 negative charges. So we take away -2, which means that our sodium ion now has a charge of +2. Here's chlorine. Chlorine has 7 electrons in its outer shell, but it wants to be full, so it takes an electron. So now we've added a charge of -1. So our chlorine now has a charge of -1. Here are some examples of different polyatomic ions. These are ions with more than one element, and thus they have different charges. There are a couple on here with just one element in them, but they're generally ions that we need to know in our work. Atoms generally have 8 electrons in their outermost shell. Let's have a general example here. We have 8 protons, 8 electrons, so we have an overall charge of 0. If we take one of these electrons away, we now have 8 plus -7, which gives us a charge of +1. If we take 2 electrons away, we have 8 plus -6, which gives us a charge of +2. Here we have an atom with only 6 electrons in its outer shell, and it's sad because it wants to have 8. It's nice and stable, it has an overall charge of 0, but it wants to have that nice full outer shell. So we add 2 electrons, and now it's nice and happy and stable. It also is now a -2 ion. But let's move on to something else. Introducing the mole. It's actually a quantity, divided by this guy, Avogadro. But moles are pretty cute. Here's Ava the mole. He will be helping us on our journey today. 1 mole of any substance is equal to 6.02 times 10 to the 23. That is a lot of stuff in just one little mole. So 1 mole of our lithium atom is 6.02 times 10 to the 23 lots of lithium atoms. Now we could have a mole of anything. We could have a mole of apples, so long as there's 6.02 times 10 to the 23 of them. So here we have 49 grams of lithium-7. We have an equation. Moles equals mass over Mr. So we have our mass in grams, which is equal to moles times the molecular mass. We have 49 grams divided by our relative atomic mass of 7, which gives us 7 moles. 7 times 6.02 times 10 to the 23 gives us 4.214 times 10 to the 35 lithium atoms. But what about other substances that are made up of more than just one element? Let's say goodbye to our lithium for now. Introducing water, H2O. How much oxygen and hydrogen is actually in a glass of H2O? Let's heat things up a little bit and capture the gas which is being released. Now let's say we started with 100 grams of H2O and we captured 22.2 grams of hydrogen. 100 take 22.2 equals 77.8 grams of oxygen. Moles equals mass over Mr. The 22.2 divided by 1 times 2, because in H2O there's 2 lots of hydrogen, is 11.1 moles of hydrogen. If we have 77.8 divided by 16, this gives us 4.8625 moles of oxygen. So now we have our moles. What we do is divide by the smallest number of moles. That gives us a ratio of 2.3 hydrogen atoms to 1 oxygen. But let's round it down, so it's 2 to 1. This gives us 2 hydrogens to 1 oxygen, which we know is H2O. Perfect, all going well. But what if we can't weigh something? How are we supposed to find out how much water we have? Let's say we have 500 milliliters of a liquid. This is equal to 500 centimeters cubed. Divide by 1,000 to give us 0.5 decimeters cubed. How do we find out how many moles there are? Here comes another equation. Moles is equal to concentration multiplied by the volume. So if we have 0.5 decimeters cubed, 3 moles, 3 divided by 0.5 gives us a concentration of 6 moles per decimeter cubed. But liquids are Pretty simple. They take up the space in anything that they're put in. What about things that aren't quite so simple, like a gas? Gas molecules move around completely randomly. Let's say we have 10 molecules of a gas. Now we still have 10 gas molecules at this volume, or this volume, or this volume. We have to make some assumptions, unless told otherwise, of course. First assumption, temperature measured in Kelvin is 298. Standard room temperature is 25 degrees Celsius, and 0 degrees Celsius is equal to 273 Kelvin. 273 add 25 equals 298. Second assumption, pressure to 101 kilopascals, which is 101 times 1000 pascals. Always remember to convert. This is equivalent of 1 atmosphere of pressure. Our third assumption is that 1 mole of gas takes up 24 decimeters cubed. So if we take up a volume of 24 decimeters cubed, and we have the number of moles, we can find the total volume in decimeters cubed that this gas takes up. This brings us to the ideal gas equation, PV equals nRT, where P is the pressure, R is our ideal gas constant, which is 8.314 joules per mole per Kelvin, T is our temperature in Kelvin, N is the number of moles, and V is our volume. Try and find the volume from this example. Remember, in PV equals nRT, volume is measured in meters cubed. Let's move on to yield. What is yield? Theoretical yield is the maximum possible product formed, assuming all reactants are fully converted. Actual yield is the actual amount of product formed found through experimentation. But there are several factors which might affect yield. This includes additional side products, impure product being formed, or the reaction not going to completion. Actual yield divided by the theoretical yield multiplied by 100 gives us the percentage yield. So we can see how economic our reaction is. Some reactions are 100% economic because it's an addition reaction, so 100% of reactants is converted to 100% of products, or because the side products are also wanted as well. This comes in a lot at a pharmaceutical level and at industry level. If it has a high percentage yield, it's good. That means we get more of the desired product. A low percentage yield means that it's not what we want. In industry, we can use a limiting reagent. If we have reactant A and reactant B, reactant A is purposely not in excess, so that it's used up first, which stops the reaction from continuing. Moving on to acids and bases. Here we have an acid and a base. How can you tell the difference? They look exactly the same. This is where indicators come in. We can use indicators to identify acids and bases of different pH levels. We've met the pH scale before back in school. 1 to 6 gives us an acid, 8 to 14 gives us an alkali. 7 is nice and neutral water. So what kind of indicators are there? For a pH range of 1.2 to 2.8, we can use thymol blue. An acid will turn red, the base will turn yellow. For a range of 2.4 to 4.0, we can use 2,4-dinitrophenol. An acid will show as colourless and a base will show as yellow. 2.9 to 4.0, we can use methyl yellow. An acid will appear red and a base will appear yellow. 3.1 to 4.4, we use methyl orange. Acid again appears red and a base appears orange. 3.0 to 4.6, bromophenol blue. Acid will appear yellow and a base will appear a nice blue-violet colour. 4.4 to 6.2, methyl red. Acid will appear red and a base will appear yellow. 5.0 to 7.0, p-nitrophenol. Acid will appear colourless, base will appear yellow. 6.4 to 8.0, phenol red. An acid appears yellow and a base appears red. 8.0 to 9.6, we use thymol blue. Acid appears yellow and a base appears blue. 8.0 to 10.0, phenolphthalein. Acid will appear colourless and a base will appear red. 10.0 to 12.0, alizarin yellow. Acid appears yellow and a base appears lilac. Again, 10.0 to 12.0, salicylic yellow. Acid will appear yellow, the base will appear an orange-brown colour. 12.0 to 13.4, trinitrobenzoic acid. Acid will appear colourless, the base will appear an orange-red colour. There is also a much simpler test, just to determine whether or not you have an acid or a base. This is where we can use litmus paper. Red litmus paper with an acid stays red. Red litmus paper with a base, it will appear blue. Blue litmus paper with a base stays blue. And blue litmus paper with an acid turns red. What exactly is an acid? So an acid contains hydrogen, which is released as a H+ ion in an aqueous solution. We have strong acid, which completely dissociates in aqueous solution, releasing all of its hydrogen as H+ ions. For example, hydrochloric acid dissociates to H+ ions and chlorine- ions. All the H dissociated to H+. There is no hydrogen left over. On the other end, we have weak acids. These only partially dissociate, releasing only a portion of the hydrogen as H+ ions. Here we have an example of methanoic acid. It's dissociating to form H+ ions and its conjugate base of CH3COO-. One of the hydrogen atoms has dissociated to this H+ ion, but then we've still got some hydrogen atoms here which have not dissociated and which have formed this conjugate base. What is a base? A base is something which neutralizes an acid to form a salt. The example I have here is actually an alkali. So an alkali dissolves in water, releasing OH- ions. All alkalis are bases, but not all bases are alkalis. Here we have a sodium hydroxide, which is our base, because it's a solid. It then dissolves in solution to form Na+ ions and OH- ions. The solution is now an alkali. OH- ions from the base plus the H+ ions from the acid creates H2O, water. This is called neutralization, where the H+ ions react to the base to form a salt and neutral water. We do have one tricky exception though. Ammonium ions act as a base. This is because the definition of a base is something that replaces the H+ ions from the acid with the metal ions. Ammonium also acts to replace the H+ ions. Here are some rules for how acids react with things. An acid plus a metal oxide forms salt and water. An acid plus a hydroxide also produces a salt and water. Acid and an alkali also forms a salt and water. Now an acid plus a carbonate forms salt plus water plus carbon dioxide. So now we know our acids and our bases and how they react to neutralize and form water. But how much base do we need to react with an acid? This is where we use titration. Titration is a method used to accurately measure the volume of one solution which reacts exactly with another solution. We use our equation of volume, concentration, and moles. If we know the volume or the concentration of something, we can work out the rest. First of all, we have to make up a standard solution. This is a solution of known concentration. We make this up in a volumetric flask. Make sure to measure the volume from the bottom of the meniscus. Here are some standard tolerances for a typical volumetric flask. For our titration, we also need a beaker. We typically place this on top of a white tile so that any colour change that might happen we can see very clearly. We also use a burette. Here are some standard tolerances for a burette that we might see in the lab. We also need a pipette and a pipette pump so that we can accurately measure how much of the standard solution goes into the burette. Filling it up to the meniscus point, then we turn the tap and slowly release our solution into our unknown solution. Once we see a colour change, we know that it has been fully neutralised. We record our data in a table like this, with the readings of our start volume and end volume for our burette. The change in this volume is what we call the titer. We carry out the titration and record the volume. We then repeat this until we have two results which are concordant. This means that two results agree to plus or minus 0.1. We do not take any further readings from this point. We then have our concentration of our base. We have our volume, which is our first concordant result, plus our second concordant result divided by 2. This gives us the mean titer. Concentration times volume equals moles. Now we have the volume of our other solution. We measured it out in our volumetric flask. We then divide this by the moles of our reacting base. This gives us the concentration. X of one solution reacts with Y of another solution. Let's move on to oxidation numbers. Oxidation numbers are a measure of the number of electrons that an atom uses to bond with atoms of another element. And like with most things in chemistry, there are rules. Oxygen has an oxidation number of -2. Hydrogen has an oxidation number of +1. Fluorine is -1. Group 1 elements are +1. Group 2 elements are +2. Group 16 are -2. And group 17 are -1. A monatomic ion has an oxidation number which is equal to the same as the charge. This is the same for a polyatomic ion. All three metals have an oxidation number of 0. Hydrogen in metal hydrides have an oxidation number of -1. Oxygen in peroxides has an oxidation number of -1. Oxygen bonded to fluorine has an oxidation number of +2. And the rule for covalent compounds is the most electronegative element has a negative oxidation number. The oxidation number for a total compound is equal to 0. The charge of an ion is equal to the sum of its oxidation numbers. A compound is oxidized when it loses an electron. It is reduced when it gains an electron. Oxidation is loss of electrons. Reduction is gain of electrons. You might remember oil rig from GCSE. This is known as redox. Here we have methane reacting with oxygen to form CO2 and H2O. We know that the total oxidation number of each of these compounds is 0. How do we find what has been reduced and what has been oxidized? We have to apply our rules. Hydrogen has an oxidation number of +1. There are 4 lots of them, so its oxidation number is +4. If the total oxidation number for methane is 0, we know that the carbon must have an oxidation number of -4. In the carbon dioxide, we know that oxygen has an oxidation number of -2, and there's 2 lots of them, so oxygen has an oxidation number of -4 here, which means that carbon must be +4. In H2O, oxygen again has an ON of -2, there's only one of them, so that stays the same. Hydrogen, we have +1, there's 2 lots of them, so it's +2. That's nice and simple. So carbon has gone from an oxidation of -4 to +4. It has lost 8 electrons, so it has been oxidized. Oxygen has gone from 0 to -2, so it has gained 2 electrons. It has been reduced. Hydrogen has gone from +1 to +1. It's unchanged. It has neither been reduced or oxidized. We do have a somewhat tricky example though. Let's look at chlorine. Here we have a reaction of chlorine reacting with hydroxide ions. We know that the chlorine total is 0. The hydroxide must have a total oxidation number of -1 because it has a charge of -1. ClO also has a charge of -1. We then have our lone chlorine ion here, so it must have an oxidation number of -1. Like before, our H2O follows the rules quite nicely. So let's have a look at our redox. Chlorine has gone from 0 to +1, but it has also gone from 0 to -1. It has both been oxidized and reduced. This is called disproportionation. It only happens with certain reactions, but it's quite interesting, and examiners sometimes like to throw it in to throw you off. And that is chapters 2, 3 and 4 summarised. Thank you for watching.